Let's draw the line through the data trace. With maths precision, we'll find the space. Hey there, welcome to Algostock. Today we are going to explore something really exciting, the math behind linear regression. Don't worry if math sounds tricky, we are going to go through it step by step together. You see, linear regression is like having a superpower. It helps us find patterns and make predictions. But how does it actually do that? Well, we'll break down the formulas and calculations so it's super easy to understand. Take a look at the normal equation on the right side of the slide. Seems big and fancy, huh? But don't worry, by the end of this, you'll get it like a pro. Ready to dive in? Let's go. Alright, to make things easier, we are going to use the same data points we talked about in a previous linear regression video. Remember those? But hey, if you are new here or need a refresher, no worries, I've got you covered. Just check out the link to that video in the description below. It will walk you through the basics and then you can come right back here to dive into the math. In our previous video, we took a deep dive into how linear regression works to minimize the residual sum of squares or RSS. That's just a fancy way of saying it tries to make the difference between our predictions and the actual data as small as possible. Now, you'll notice a graph on the right. It's showing the sum of squared errors versus the intercept of the line, which forms a parabola shape. You might remember this kind of graph helps visualize how we adjust the line to minimize error. And don't forget, the tangent line you see there has a slope of 0. That's the sweet spot where we find the best fit. But no worries if this seems familiar, we covered this more in depth in the previous video. Here, you'll see that we are looking for the point where the cost function curve flattens out. Why? Because this is where the slope of the tangent line is 0. It's like finding the perfect spot where the curve levels off, giving us the best fit for our data. Pretty cool, right? This point is where our model performs its best. Alright, let's switch gears. In this video, we are going to dive into the mathematical equations that make linear regression tick. You might remember the graph we have seen before. It's still here to remind us the concepts we have covered. But today, we are focusing on how those equations work behind the scenes. Ready to get into the math? Let's uncover the secrets of how linear regression really works. For our example today, we are keeping things simple by focusing on just one feature or one x variable. The general equation of a line looks like this: y equals theta 0 plus theta 1 x1 plus theta 2 x2 plus theta I xi. But since we are using just one feature, we can simplify it to y equals theta 0 plus theta 1 x1. On the graph, you'll see 5 randomly selected data points from the California dataset we used in the previous video. And check it out. I've plotted a line here to give you a visual feel of linear regression. This is the same line we discussed before. It's like putting everything together in a more straightforward way for you. Now let's take a closer look at why linear regression aims to minimize the residual sum of squares or RSS. We use RSS to measure how well our line fits the data. The formula for RSS is summation of the squares of y hat minus y. That might sound a bit complex, but basically it's the sum of the squared differences between our predictions and the actual values. On the graph, you'll see the same data points and line from before. I've added straight lines from each data point to the line, showing these differences. These lines represent the errors we are trying to minimize. The smaller these lines, the better our line fits the data. Pretty neat, right? Alright, we are about to dive into something really exciting, derivation. This is where we start breaking down the normal equation from our RSS equation. Get ready to see how we turn those ideas into actual equations that help us find the best fit line. On this slide, you'll notice the line equation at the top left, keeping it handy as we work through the details. Now, let's talk about what x represents. In our context, x is a matrix where each row stands for a training data point and each column corresponds to the features of our data set. Think of it like a big table where we keep all our data organized. This matrix helps us apply our equation to the data efficiently. Now that we have got the matrix X in mind, let's see how it looks with just one feature and 5 data points. Here you'll see our matrix X with 5 rows and 1 column. Each cell in this column represents one of our data points like x1, x2, x3, x4 and x5. It's a simple but powerful way to organize our data so we can use it in our equations. This matrix is our starting point for deriving the normal equation. Just like with x, theta is a column vector where each entry represents a coefficient of the line we are aiming to find. On this slide, you'll see theta as a 1 column 2 row matrix with values theta 0 and theta 1. These are the same coefficients we used in our linear equation at the top left. This matrix helps us adjust the line to best fit our data. Now we are setting up everything we need to derive the normal equation. To get our predicted values matrix y hat, we need to perform a simple operation, the dot product of theta and x. On this slide, you can see how it works. We take our matrix theta, which has theta 0 and theta 1, and multiply it by our matrix x. This gives us a new matrix where each row is calculated like this: theta 0 plus theta 1 x1, theta 0 plus theta 1 x2, and so on. The result is a matrix of predicted values y hat with values like y1, y2, y3, y4, and y5. This is how we generate our predictions using the line equation. But wait a second, we have hit a small snag. Our matrix theta includes theta 0, which represents the intercept. However, matrix X doesn't have a column for this intercept. So, how do we handle this mismatch? Great question. To solve this, we need to adjust our matrix X to include a column that accounts for the intercept term. This way, we can properly calculate our predictions and keep everything in sync. Let's see how we fix this. To solve the issue, we simply add a column of 1s to our matrix X. This addition allows us to include the intercept term. So, instead of just having theta 0 and theta 1 x1, we can write our equation as y hat equals theta 0 multiplied by 1 plus theta 1 multiplied by x1. By adding a column of 1s, we make sure that our matrix X has a place for the intercept term. This way, everything lines up perfectly for our calculations. Now, if you want your predicting line to pass through the origin, meaning it has no intercept value, here's how it changes. In this case, our equation of the line simplifies to just y hat equals theta 1 x1. You'll notice that our matrix theta now includes theta 1 with no intercept term. This setup makes the line go through the origin, which can be useful in some situations. But for our case, we'll stick with including the intercept term. So, we need to add a column of 1s to our matrix X. This adjustment ensures that we account for the intercept in our linear equation. By doing this, we can correctly model our predictions with a full equation including both theta 0 and theta 1. Ready to see how this looks in action? Let's move on. Now that we have added a column of 1s to our matrix X to account for theta 0, we can easily compute our predicted values y hat. In matrix form, our equation looks like this: y hat equals x theta. This matrix format simplifies our calculations and keeps everything neat and organized. It's like putting all the pieces together to get our predictions in a smooth and efficient manner. Let's break down what each part of the equation y hat equals x theta represents. Y hat stands for our predicted values. These are the outputs our model gives based on the inputs. X is the matrix of input features. We have added a column of 1s here to account for the intercept term. Theta is the vector coefficient. This includes both theta 0 and theta 1. Putting these together, our equation helps us predict outcomes efficiently using matrix operations. Let's get into the math and start our derivation. We'll start with the residual sum of squares formula. This formula measures the difference between our predicted values y hat and the actual values yi. Next, we can rewrite this in matrix form. Here, x theta represents our predicted values matrix and y is the actual value matrix. To make it even simpler, we use this form. This equation uses matrix notation where x theta minus yt means the transpose of x theta minus y, and multiplying it by x theta y gives us the squared sum of residuals. It's a compact way to express the same idea and helps us with further calculations. Expanding this gives us transpose of x theta multiplied by x theta minus transpose of x theta multiplied by y minus y transposed multiplied by x theta plus transpose of y multiplied by y. Using matrix properties, we can further simplify to RSS equals theta t x theta minus 2yt x theta plus yt y. I would request you to pause this video for 5 seconds to glance through the steps so far. Finally, we get RSS equals x transposed x theta square minus 2 times y transposed x theta plus y transposed y. This expanded form helps us see how each term contributes to the total RSS. Let's put everything together and find out how we get to the optimal solution for our line. First, we look at our final RSS equation in the top left corner. To find the best fit line, we need to minimize the RSS. The key to this finding is where the gradient or the slope of the tangent is 0. This is the point where RSS stops decreasing and starts increasing, meaning we have found the minimum value. Take another look at the graph of the parabola we saw earlier. This graph illustrates how the sum of the squared errors changes with the intercept. The minimum point on this curve is where the tangent's slope is 0. This point gives us the optimal solution for our coefficients where our model fits the data best. So, by finding where this gradient is 0, we can pinpoint the best possible fit for our line. It's like finding the perfect balance where our predictions are most accurate. Now, this equation represents the condition we need to find our optional solution. It tells us that to minimize the RSS, the derivative of the RSS with respect to theta must be 0. Essentially, we are looking for the point where the slope of our RSS curve is flat, where it levels out. This is the mathematical way of saying we have found the minimum point of our error, ensuring the best fit of our data. Let's dive deeper into solving for theta using the gradient condition we discussed. We start with our expanded RSS equation, then we take the derivative with respect to theta. To isolate theta, we solve for it. Here, xtx minus 1 represents the inverse of xtx and xty is a matrix multiplication of the transposed input features with the actual values. This final equation shows us how to calculate the optimal coefficient theta that minimizes the RSS. It's like solving a puzzle to find the perfect fit of our line. Now that we have completed the derivation, it's time to put it into practice with a real example. We'll use the normal equation to find the slope and intercept of our data. Remember the normal equation? We also have a graph with 5 data points and we have set up our matrices x and y. Here's what the matrices looks like. We'll plug these matrices into our normal equation to compute theta, which gives us the values for the slope and intercept of best fit line. This is where the math meets the real world. Now, let's dive into the calculation. We'll start by computing the first term of our normal equation, getting our matrix x and taking transpose of it. The transpose simply flips the rows and columns of x. This is the first step in our calculation process. Next, we'll use these matrices to compute xtx. We start with the matrix multiplication of xt and x. Here's how we calculate each cell in the resulting matrix. Multiply the first row of xt by the first column of x and add these values together. So, the value of the first cell in our resulting matrix is 5. For the second cell in the first row, you would multiply the first row of xt by the second column of x. By performing these multiplications and additions for all cells, we complete the matrix xtx. This step is essential for our next calculations in the normal equation. Let's proceed with filling in the rest of the values and continue our derivation. With this complete, we are ready to move on to the next step in finding our optimal coefficients. Now that we have our xtx matrix, the next step is to find its inverse. We use the formula for the inverse of a matrix which involves two key components, determinant of xtx which gives us a scalar value and the adjugate of xtx which is the transpose of the cofactor matrix. This means we first calculate the determinant of xtx matrix, then find the adjugate and multiply these to get the inverse. With these inverse matrix, we are one step closer to solving our normal equation and finding our optimal coefficients. Let's calculate the determinant of our xtx matrix. First, multiply 5 by 8358. Next, multiply 192 by 192. Subtract the second result from the first, so the determinant of xtx is 4926. Next, we calculate the adjugate of xtx matrix. The adjugate or adjoint matrix is the transpose of the cofactor matrix. The top left entry 8358 and the bottom right entry 5 are the cofactor determinants for their positions. The off-diagonal entries are adjusted by changing the sign based on their positions in the matrix. The adjugate matrix is used in conjunction with the determinant to find the inverse of xtx. Let's proceed to calculate the inverse using this adjugate and the determinant we have calculated. To get the desired matrix, in order to calculate the second term of the normal equation, we take x transpose and matrix y to get the product of matrix x transpose times y. Finally, we can take the product of both the terms we just calculated to get the value of matrix theta. We have now calculated everything and we are ready to find our final result. our optimal coefficient theta are 2.6795 and minus 0.0203. This means our line equation, which minimizes the residual sum of squares, is y hat equals 2.6795 plus minus 0.0203x. In the graph, you can see the best fit line plotted alongside our 5 data points. This line represents the optimal fit that minimizes the error between our predicted values and the actual data. This line is our final result from the linear regression model. We have taken our data through the math, calculated the best fit line, and visualized the result. This is how linear regression helps us find the best fit for our data. Thanks for watching till the end. I hope this video has given you a solid understanding of the core concepts of linear regression. If you are curious about how to implement these ideas in Python and see them in action, be sure to check out our detailed coding tutorial linked in the description below. If you enjoyed this video and want to see more like it, don't forget to subscribe and stay tuned for future content. Until next time, stay curious and keep exploring the math.